All right. Okay, so in principle, this lecture should have been the very first one, but it worked out this time since Ken wasn't here last week to do my thing today and then his thing this afternoon. So basically, for me, you're going to get the theory kind of viewpoint. Then the next lecture will be Ken giving you the experimentalist sort of viewpoint, and then you'll do the radiometry lab, or at least one of them this afternoon. So basically what I'm going to do today is talk a little bit about just what the heck is light. That's our philosophy section for the course. And then I'll talk about radiometry, which is simply the science of how you quantitatively describe and measure light. So we have to figure out how to describe, how much light is there, where is it going, what wavelength or frequency does it have, and so forth. And then, as I mentioned, Ken will then discuss the measurement side of it in the next lecture, and then you'll do it in the lab. And of course, this is the first chapter in the Ocean Optics web book, or the Ocean Optics book, if you want to see all the details. I'm not going to go through this, but I have a little table here of people's viewpoints of light going back a couple of thousand years. And as we'll see in a minute, it has kind of alternated between it's a particle, it's a wave, or it's both a wave and a particle, well, it's neither one, whatever. There's kind of a half a page or a page on each one of these things on the web book. If you want to look it up, it's kind of interesting reading to see how people's viewpoints have changed over the centuries. But I will talk about just a couple of experiments. If you go back to the ancient Greeks, this fellow Democritus, from whom we get democracy, he decided that everything was a particle or made up of particles, and it didn't matter whether it was a rock or light or your soul or whatever, everything was made out of particles. And that kind of went along for 1800 years or so. And Isaac Newton thought light was a particle. And the reason is when he was doing his optics experiment, he couldn't see light bending around a corner, whereas sound bends around corners very nicely. If you're around the corner there, I can still hear you talking. But if there's a light bulb around the corner, I'm still in the shadow here. So Newton simply wasn't able to observe diffraction, for example. So he thought light was a particle. And then there were other people thought, yeah, it's a wave. But finally, they thought the issue was settled when Young did this classic two-slit diffraction experiment, actually did it in 1803. And so he was able to create coherent light waves coming in. Coherent means these guys are all the same wavelength, they're all in step, all going in the same direction. And he did this two-slit experiment, which is trivial with a laser, was actually quite difficult in the old days to create coherent light. But he did it, and he observed these patterns of bright and dark bands here. And there's no way to explain that if light is a particle, but it's easily explained if light is a wave. So that sort of proved that light's a wave. Well, then it oscillated back and forth. Some people still thought it was a particle, but most decided it was a wave. And then in 1923, Compton did this experiment where he shined light, which was actually in his case X-ray wavelengths, onto atoms, and the light would knock an atom or knock an electron loose, and he was able to derive this little simple formula that said when the light comes in and an electron bounces off and the light bounces off, it both shifts the wavelength of the light from the incident wavelength, and there's an angular distribution of the light here. And so he was able to get this great experiment or great agreement between the theory and the experiment. And there's no way to explain this if light is a wave. So this conclusively showed that light had to be some kind of particle. Well, then it's just gotten worse ever since. So then the question is, well, if light's a particle or it's a wave, what would you get if you did the two-slit experiment, but you just sent one particle of light at a time onto your screen here? Yeah, Ben.
Random dots on the screen.
What?
Random dots on the screen.
Yeah, but are they going to show any kind of pattern, or will they just be like, if a particle goes through this hole, there'll be a little stack of points here, and if it goes through this hole, maybe there'll be a little stack of points here.
Yeah.
Okay, well, what you actually get is exactly the same interference pattern. So after you send a few photons in, you know, they begin kind of collecting in certain areas and not much in other areas, and you get exactly the same interference pattern, one photon at a time. Now, this fellow Feynman, who's one of the great physicists of the 20th century, he calls this the fundamental mystery of quantum mechanics. If light's a particle and it just goes through, or at least a classical particle like a little ball, it can only go through one hole at a time and you don't get interference. If you get interference, it has to go through both holes simultaneously so that what's coming through each hole can interfere with itself. And this is really, really weird. Here's an actual CCD images of this experiment being done. And there's a web link here. This is on YouTube. There's about a 10-minute video where they talk about how they set the experiment up, and you actually see the time series of the points developing. So at 3 minutes, they've sent about 24 photons or particles of light through the screen, and it doesn't seem to show any pattern. And a few minutes later, yeah, still not much of a pattern. But after almost half an hour, you're now starting to see a pattern. And here's 6 hours. You're getting exactly the same interference fringes as you got from the wave model. And this simply, there's no way in classical physics to explain this. So the conclusion here is that if you're going to try to think about this interference from a single photon at a time, you have to abandon the idea that a photon or particle of light, whatever it is not a little localized particle that goes through one slit or the other. And so you just have to just get rid of that image of photons as being little balls of light bouncing around. Because whatever they are, even one of them, it can go through both slits at the same time and come out the other side and interfere with itself. And then in what is called quantum molecular dynamic calculations, which is the most successful theory in physics, the way it does its calculations is if I emit a photon here and you observe it from your instrument over there, the photons, it simultaneously takes every path possible through space and ends up over there. And it's not until you compute each one of those paths and add them all together that it looks like the light went in a straight line from here to there. And there's this book by Feynman called The Strange Theory of Light and Matter, where he talks about this, and he actually shows you some experiments that you can do that shows that, like, when light's reflecting off of this surface and going over here, we think of it as it comes here and it reflects off there. It actually bounces here, 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 here. It bounces over there and reflects up there. And then you add all those calculations together and it looks like it just went in a straight line, but that's not what it really does. So anyway, the other thing you have to abandon is that the idea that a photon takes a particular path from one point to another. It actually sort of some way or another fills all of space and eventually gets over there. And so all you can say about a photon is you can say where it was created. So a particular atom in this light bulb emitted a photon. And you can say where it was collected. So it was on a particular pixel of a CCD array over there. You can say nothing about the path the photon took from where it was created to where it was observed. And it seems crazy, but that's simply the way it works. And Feynman actually had this statement that said, nobody knows what a photon is, and it's best not to think about it because it's just nothing that can be explained in everyday terms. So in physics, we've gone from, oh, it's a particle, no, it's a wave. Well, it looks kind of like it's both a particle and a wave, but it really behaves like neither one. And the only comparable thing that I know of is in Buddhist philosophy. In Western philosophy, we think of a statement as either being true or false. I'd say whatever. There's this fellow, Nagarjuna, who lived about 100 AD, Buddhist theologian, and he came up with what's called Nagarjuna's tetralemma, which says a statement can either be false, or it can be true, or it can be both true and false at the same time, or it can be neither true nor false. And this is kind of the same thing. Light's a particle, it's a wave, no, it's both, no, it's neither. And that's just the way it is. Fortunately, the only thing you really have to know about a photon is that they have a certain amount of energy, and that can be described by either its frequency or wavelength. It has a linear momentum equivalent thing. It has angular momentum, and it has a state of polarization. And that's sort of all you need to know. And things like position and path and time for photons are just not even defined in physics. So if you have a basketball, you can say the basketball is in that corner of the room. You can't say the photon's in that corner of the room. And I've been beaten on severely by the physicists for using the word photon on the web book and stuff, because they say, no, that's just all completely wrong. So if you'll notice when we do the Monte Carlo lab, my Monte Carlo code no longer traces photons, it traces rays, light rays, like this beam of light here. And then the physicists leave me alone. Okay, so anyway, enough said about what light is. It's just, there's just no answer in everyday terms. But if you want to go back and read that first little section of the web book, there's about 8 or 10 pages of all these philosophical viewpoints, and you can watch the little film and stuff. It's worth doing. It'll only take you 10 minutes. Okay, all right, come on. Now this thing has quit advancing. All right. Okay, and now let's try it again. Okay, there we go. All right, so there it is. So anyway, this little strange story of light and matter is definitely worth reading, and you can follow up on these other things here. And just keep in mind that almost everything you see written in a freshman physics book or you find on the web where it says a photon is whatever is probably wrong. Okay, so really what you need to know is that photons, whatever they are, they have a certain amount of energy, they have some frequency or wavelength or equivalent, and they have energy, which is given by Planck's constant times the speed of the light over the wavelength, or just Planck's constant times frequency. So this is the only formula I've ever bothered to remember, is energy equals hc over lambda. I use that all the time. They also have a linear momentum, which is Planck's constant times the frequency over the speed of light, and they have angular momentum. So notice the energy and the linear momentum both depend on the frequency or the wavelength. The angular momentum is constant. It's the same for every photon, no matter what its wavelength is. If we want to use those formulas and do a little example calculation. So a typical day, you go outside on a sunny day, there's something like 400 watts per square meter in the visible wavelength range. Now, today it's probably more like 300 because it's hazy, but if it's a bright sunny day and the sun's straight overhead, maybe it's 600, but something like that sort of number. And so let's just assume that we have green light here, 550. How many photons does it take to make 400 watts per square meter? Well, we use the energy we have, the 400 watts a joule per second per square meter. So there's our energy coming in, or the power, and then each photon has an energy of hc over lambda. So you go look up those numbers, plug those in, and that's something like 10 to the 21st photons per square meter per second. It's just an enormous number. So you don't see effects of individual photons getting absorbed by your thermometer. It just heats up as the day goes on. And so that's how many is hitting each square meter per second, this huge number of photons. And then if you think of, well, a cubic meter of water, how many photons are actually in a cubic meter of water right up at the sea surface at any given moment? Well, you have the 10 to the 21st photons coming in, but they're moving through the meter of water at the speed of light in water, which is c over index of refraction. So you do the arithmetic there, and it's something like order of 10 to the 12th photons per cubic meter at any given instant. And that's just coincidentally about the same number of phytoplankton that are in a cubic meter of water. So it's like there's one photon per phytoplankton at any moment, but of course the phytoplankton sit there and the photons are moving through. So each phytoplankton gets hit by millions and millions of photons every second. But you can do these little kinds of calculations and they get, kind of fun to play with. Okay, so on to more quantitative stuff now, radiometry, which I said is just the science of measuring electromagnetic or radiant energy. So if you want to do that, you have to figure out how to specify directions, how do you describe how much light there is in some way or another, and figure out where it's going. And the fundamental quantity that does this is the radiance. And you've been hearing that word now for a week without maybe really knowing exactly what it is. But in theory, radiance is the starting point for all of the theory, because any other measure of light, like an irradiance or PAR or whatever, can all be derived from the radiance. So this is the fundamental quantity. Now, these irradiances that we'll talk about in a minute, they're often easier to measure, so they get used. And the radiance maybe has more information than you need for your problem, so you don't really have to measure it, but you can get by with measuring something simpler. Okay, so we've seen this chart before, and you're going to see it at the beginning of most of my lectures. Last week was all the inherent optical properties: absorption, volume scattering function, measuring all these backscatter coefficients, total scatter, beam attenuation, all of that stuff. So today we're going to be in the red box here. And you notice if you know the radiance, then all these other things, irradiances and PAR and such, you can compute from the radiance. So today's lecture is defining all of these terms that's in this box. And there's two kinds of instruments that generally get called thermal and quantum. A thermal instrument, you make some sort of measurement of the light, and the response of the instrument is proportional to the energy that's absorbed by the instrument. So a thermometer is a thermal instrument for measuring how much light's there, and the liquid or whatever it is in the thermometer absorbs energy from the light, it heats up, and that changes the column of liquid in the glass, or it changes the angle of a bimetallic coupling bends. Yeah.
A thermometer measures light.
Well, you can use it to measure light. So if I want to make an instrument to measure how strong the light is in this room, I could just take an old-fashioned mercury thermometer, put it at the end of a little tube here, and if I pointed at the light there, the thermometer would heat up from the light that's being absorbed faster than if I point it down at the dark spot here where there's not much light coming in. So that's the idea there. It's just a way of measuring how much energy was absorbed by the instrument and turning that into some measure of light. Then there's quantum detectors where the instrument response is proportional to the number of photons detected. So the typical thing there is like a CCD array in a digital camera or a video camera. And it's simply counting on this little pixel here, I recorded 1 million photons, and on the pixel next to it, I recorded 10 million. So the light that hits this pixel was 10 times brighter than the light that hits the other pixel. And then you some way calibrate that and turn it into what you're interested in. That's just the two different classes of detectors. Okay, so to figure out where the light's going, we need some way to describe directions. Colin went through this, but I'll do it again. So we're going to pick some coordinate system, X, Y, Z, for our particular problem. And in the ocean, you know, Z might be downward and X might be pointing towards the sun or downwind, whatever. But we just pick a coordinate system. And then we want to specify some direction, which I use as C here. And I can either describe C, this red vector here, as having components of so much in the X direction, so much in the Y, or so much in the Z direction, or I could say it has some R, theta, phi coordinates and think of it in a spherical coordinate system. There and they're equivalent. So the C is a unit vector just giving me direction. Unit vector meaning it has magnitude or length of 1. So if I want to figure out the relationship between the X, Y, and Z components and the R, theta, phi components, it's the old standard spherical coordinate system thing, which you've probably already seen, but I can always write C as being the X component in the X direction, so much in the Y direction, so much in the Z direction. But then I can look back up here and say, well, if I have this vector and I drop a perpendicular over to the Z axis here, that's parallel to the XY plane, well, that's the Z component. But if I just look at this right triangle, it's kind of have to remember this is actually a right angle here. Then this is 1, and this distance here would just be cosine of theta, because the cosine is the adjacent over the hypotenuse. So the Z component is just cosine of theta, or theta is the inverse cosine of the Z component. And then if you drop a perpendicular from the point down into the XY plane, that's the same as this distance. Well, that's just the sine of theta. And then if you take this and resolve it along the x-axis and the y-axis, and keeping in mind that those are right angles, then how much this distance is just this much times the cosine of this angle. So the x component is sine theta sine phi, and the y component here is sine theta cosine phi. So you can write the unit vector as being this much in the x hat, this much in the y hat, and this much in the z hat, where we now use the angles theta and phi, and theta is measured from the plus z axis, and phi is measured from the x-axis by a counterclockwise rotation if you look down the z-axis towards the origin. So anyway, you end up with these nice little equations. You'll often see that people use mu as being the cosine of theta as their polar variable rather than theta, and you know, they're all equivalent. Now, in my work, always in radiative transfer theory, the direction of light is always the direction the light is traveling. The experimentalists will publish a paper and they say, we measured the radiance in the theta phi direction, and their theta phi is the direction the instrument was pointing to measure the light going in the opposite direction. So it's always confusing. It's easy to convert back and forth that if my light is traveling in this direction, then to measure, I'm looking in the opposite direction, which is pi or 180 degrees minus that direction, or phi is if the light's going this direction, then I'm going to point my instrument looking the opposite direction. So that's just phi plus pi. So it's sometimes confusing in papers when they just say, here's the radiance as a function of theta phi, and they don't tell you whether that's the direction the light was traveling or the direction their instrument was pointing. Okay. Common thing is we need to know the scattering angle. So I start out here, I've got my coordinate system. I start out with a photon, it's going in the C prime direction here. And right here, it hits a particle and it scatters off into some other direction. So now it's the scattered particle has some theta phi direction in the XYZ coordinate system. Well, what's the angle between those two? Okay, you remember the dot product of two vectors, A dot B is magnitude of A times magnitude of B times the cosine of the angle in between. Well, now our two vectors are an incident direction C prime and a final direction C. Those both have unit magnitude. So the dot product of two unit vectors is just the cosine of the angle in between, cosine of psi. And then I can go write each one of those as sines and cosines and whatever, and plug into the dot product. And you come up with either the cosine of psi being the product of the x components plus the y plus the z, or the thing that's most useful is that the cosine of the scattering angle, given these two directions, is just the cosine of the theta prime times theta, and then sine of theta prime sine, and then the cosine of the difference in the phi directions. So that's the one that's been living in my head for 50 years now, and I use it all the time. My convention when you read Light and Water or the web book is that a primed variable is always the incident or the unscattered direction, and the unprimed variables here, C or theta, those are always the final or the scattered directions. So, you know, you go read somebody else's papers, and maybe they do it backwards. That's my convention. And it doesn't really matter how you do it, but pick one convention and stick with it for the rest of your life. And it'll just make your life easier. Okay. So Colin talked a little bit about scattering our solid angles. So once again, the plane angle, theta here, is really by definition, it just means I have a circle of some radius r, and if I take a little arc length on the circle circumference, and then I divide by the radius, that this angle theta is just by definition L over R here. So it's just a non-dimensional number. It doesn't matter how big the circle is, the radius divides out, and you just get this angle theta, which is really a non-dimensional number, but we say it has units of radians to remind us that if the number is 3.7, it's a measure of 3.7 angles. And of course, there's 2 pi times the radius is the circumference of a whole circle. So a whole circle has an angle of 2 pi radians. Then the solid angle, as Colin said, it's the same thing. You think of having a sphere of some radius r and some patch of area on the surface of the sphere. So the solid angle is just by definition the area of this little patch here divided now by the radius squared. So once again, it's a non-dimensional number, but we call them sterradians, where ster means solid. And because a sphere, the area of a sphere is 4 pi r squared, and then you divide by r squared, there's actually 4 pi sterradians in a sphere, or the whole, you know, all directions together. Okay, so as an example, if you think of yourself sitting down in the middle of the earth, and you're looking up and there's like the lower 48 states, they have an area of about 8 million square kilometers, and the radius of the Earth's about 6,300 kilometers. So you just plug in the number area over 6,300 squared, and you come out with the solid angle of the 48 states as seen from the center of the Earth is about 0.2 sterradians. So there's nothing complicated there. Okay, if we want to actually say, I got this sphere, and you know, I have an area that goes from, you know, this latitude to this one, and this longitude to that one, you know, what's the area of that surface, and what would the solid angle be? Well, once again, you can pick your XYZ coordinate system. Here's a sphere of radius r, and there's some little patch of area on the surface here. And if you look at, this direction here, that's just a circle of radius r. And so this distance here is a bit of arc length on the surface. And that arc length is just r times d theta. And then once again, just like the figure a minute ago, this distance right here is r sine theta. That distance right there would be r cosine theta. But anyway, r sine theta, and then we are moving through a little distance d phi here. So this side of the little rectangle is r sine theta d phi. And multiply those things together, you get the area. And then if you divide by r squared, the r's go out, and you get that this little bit of solid angle, or the solid angle corresponding to this little element of area there, is just d omega, omega solid angle. It's just sine theta, d phi. Or if you use mu instead of theta, it's just d mu, d phi. So now the thing you have to do is, I've designed this instrument, and it's this long, and it's got a hole in the end that's this big, and my detector's back here. Well, what's the solid angle of that little circle? Well, you can think of moving this little patch of area up to the North Pole here. So now theta is just the half angle of a little cone, and you can say, well, let's integrate from angle theta equals 0 out to say 5 degrees, and then we'll integrate all around in phi direction, plug that in, do the integration, and the solid angle of a little patch of area at the North Pole here is just 2 pi 1 minus cosine theta. And so I use that once again all the time. So if your instrument has a field of view that's say 5 degrees, then you plug in 5 degrees, and there's what the field of view of that instrument would be. So once again, this lives in my brain, and I use it all the time. Okay, so now with that in mind, we're going to actually build an instrument now to measure light or measure radiance. So we've got a detector of some sort that will give some kind of response when light shines on it. That could be a thermal detector, it could be a quantum detector. We only want to know how much light is coming from a particular direction. So we put this detector inside some kind of tube. And so if light comes in from the side, it'll hit the insides of the tube, and we can put some little baffles in here that'll keep the light from bouncing down inside. We'll paint the inside of this thing black. And so light coming in at too great of an angle will not make it to the detector. But the detector's here, there's a little hole in the end here. So the light that's coming in almost straight in within some little field of view, I call it alpha here, that light will go right through the middle of everything and be detected. Now, along the way, we may have a filter to measure the light's particular polarization. We'll probably have a wavelength filter in here that will get rid of all except a narrow band of wavelengths. And then we'll end up with a measure of the light of a particular polarization, and say from 400 to 410 nanometers. And then that's what we're interested in. So we're going to measure the radiance as a function of position, wherever my detector is at the time I made the measurement, and for the theta and phi direction where I'm pointing the detector, and as a function of wavelength. Now, you often in these instruments, you have a diffuser here, and that's a piece of usually opal glass that, light shines through it. It's like frosted glass. So I may be seeing bright light coming in on one side here, maybe not so bright here, but it hits the diffuser. And then behind the diffuser, the light field in here is uniform. So I just have to measure a little bit of the light field. And if this little detector area is a tenth of the whole area here that could be seen by light, then I just measure a tenth of what's there and I multiply by 10 to get the grand total. Okay, so that's why there's the diffuser there, is so I don't have to build a big detecting surface. I can just make a little one, which costs me less money. Now, that's a traditional design. It's called a Gershon tube, named after this Russian fellow Gershon, who built the first radiance meters back in the 1930s. A more modern design, you may have a photodetector back here. You may have a lens out here and block here with a little pinhole through it. So the light that comes in just the right direction, the blue light here, will get focused by the lens down onto the pinhole, come out the other side, and go into my detector after it goes through any polarizers or filters. The light that's coming in off axis, the red light, will get focused by the lens, but it'll miss the pinhole, so it doesn't get through to the detector. So either one of these things is what gets called a well-collimated radiance detector. And those are pretty common. So there's the Hubble Space Telescope. It's a well-collimated radiometer. It's only seeing one particular little direction here where it's looking. There's a radio telescope, different wavelength, but once again, it's only detecting radio waves from a very small set of directions. The camera, there's a Gershon tube, the human eye. Now you think, well, wait a minute, the human eye is detecting light coming from all directions, but the light coming from a particular point there goes to one little spot on the retina, and the light coming from over here goes to a different spot on the retina. So each little part of the retina is itself a well-collimated radiometer, and then I can build up with my brain a picture of what's out there with very high spatial resolution. Okay, so back to this now. We have this instrument, whether it's an old one or a new one, and we want to actually measure the radiance. Well, what you do is you turn on the instrument, you know what directions it's pointing and all of that. You make a measurement for some time delta t, and maybe that's 1,000th of a second, maybe it's an hour. The detector area here has, or the diffuser area, has some area delta A. You know what that is. You know what the field of view of the instrument is, so you can compute the solid angle. You know what the wavelength bands of your filter is, so you can know what delta lambda is. And you turn this thing on, and after a while, you've measured some amount of energy, delta Q. That's all there is to it. So now you have energy per unit time, which is actually power, per unit area, per unit solid angle, per unit wavelength interval. So the units of radiance are watts per square meter per steradian per nanometer. And this, if we're in general, you know, you can move this around in 3 dimensions. In hydrolite, we're going to assume everything's horizontally homogeneous. So it's just going to compute the radius as a function of depth, direction, and wavelength. But these are the units. And you'll see the word spectral radiance. Spectral generally means per unit wavelength interval. But some people will write a paper and it'll say we measured the spectral radiance. And what they mean there is we measured it as a function of wavelength. Can be confusing, but that's just the way it worked. Okay, so in general, you really have to measure light, take care of its polarization quantities, and there's a 4-element vector called the Stokes vector, which has elements I, Q, U, and V. The first element of the Stokes vector, when people do polarization stuff, they always call it I, but that's the radiance L to us. The I component, or the radiance, is just the total radiance, and I don't care what state of polarization it is. Then the Q and U components are used to figure out the linear polarization. Is it this way? Is it this way? Is it something in between? And the V component specifies whether it's either left circular or right circular. So Ken will have a lecture on polarization later, so I'm just going to let it go at that. But IRradiance is the first component of the Stokes vector. It's the total without regard to the state of polarization. And so for the moment, we'll just forget about polarization. So there's what you're actually measuring in an instrument. And that usually gets called an operational definition, meaning, you know, this is how you make an instrument and operate it. It actually gets numbers out. The theoreticians will often say, well, let's let the delta T, the delta A's and all that go to zero. And this really looks like a fourth derivative of energy with respect to time, area, solid angle, and wavelength. So then you'll see a textbook might say, if you take the radiance and you integrate over these intervals, or integrate here over the intervals, then you'll get the total energy detected. So that's what's going on there. I live in this world, Ken lives in that world. Okay, so let's look at some radiance distributions. It's a bit hard to plot, even in the simplest case, like coming out of hydrolite, it's going to be a function of depth, theta, phi, and wavelength. So you've got 4 variables, and it's hard to get that on a 2-dimensional piece of paper. So you'll almost always see something like this. Here's radiance at a few depths as a function of wavelength and for one particular viewing direction. So this says as a function for the zenith viewing direction. So I'm looking, pointing my instrument, looking upward, and I'm looking at radiance going straight down. And so I called it LD here to remind me that this is downwelling radiance going straight into the water as a function of depth and wavelength. And I have the black line is the value in air. And then I go put my instrument just below the water, still looking up. And something weird happens. Notice that in the water here, just below the surface, the radiance is actually greater than it was in the air. Well, that's, at first look, sounds counterintuitive, because I'm in the air, here's the sea surface, I'm looking up at the sky, and then I go just below the surface. Well, some of the light that I was measuring is being reflected backward by the surface. So why would the radiance increase when I go into the water? So just tuck that away as something unexplained at the moment. Notice there's also some bumps appearing out here that are not here. They're not in the sky, they're not in the values just below the sea surface, but by the time I get down to 50 meters or 200 meters, I have this weird bump out here. So you have to worry like, well, what's with that? It wasn't up here, how come it's down here? Well, you guys already know the answer is fluorescence, chlorophyll fluorescence, but you might not know the answer to that one. So I'm going to leave that as a mystery. And by the end of the class, you should be able to answer it. Here's another plot of radiance. Now I pick one wavelength and I pick several different viewing directions and plotted things as a function of depth. So LD, purple, the zenith of viewing. So the instrument's looking up and that's really bright. And then if I'm in the water looking horizontally, so let's say the light there is the sun. So I point my instrument this way, and so it's getting some sunlight coming in and getting scattered into my instrument. Or finally, I point my instrument straight down, and that's looking at light that got below me and got back scattered back up. So it's a much smaller value than the downwelling light. And looking towards the sun at right angles to the sun or away from the sun, it goes from bright to not so bright to even less. So you look at this and say, well, okay, that sort of makes sense, except notice that as I go into the water here, for a couple of these directions, the radiance actually increases for a while with depth, and then it begins decreasing. But other directions, it just decreases from the surface all the way down. So you have to kind of wonder, like, what's going on here, that if I'm viewing the zenith radiance and I go into the water and it gets brighter and brighter as I go down for like 5 meters or so, and then it starts getting darker again. You ought to think intuitively, I go in the water, the light that's getting in there, some of it's being absorbed, so it ought to just keep getting darker and darker. But that's not what happens. And so by the end of the class, you should know the answer there. Okay, here's another plot where I picked as a function of polar angle, that is this angle, and I'm looking in the plane of the sun. So if the light is the sun, I'm going to be looking in this plane here, not in this one or this one. And it's a function of wavelength, and then at a particular depth of 10 meters. Okay, so here's wavelength, blue to green to red along this axis. Here's my viewing direction. Now, I always stick a little V on the theta to remind me that this is now viewing direction, not the theta that's the direction the light's going. Now, in my axis in oceanography, we always like to pick Z positive downward. So you're going to measure depth from 0 at the surface and increasing downward. If you were an atmospheric guy, you'd pick at 0 at the surface and increasing going upward, but we're oceanographers. Okay, so viewing direction of theta V equals 0. A polar angle of 0 is looking straight down, measuring the light coming straight up. And the magnitude is not much. Out here, it's somewhere roughly 180 degrees. This is 180 degrees. My viewing direction is looking upward at the sun or other light that's going downward. So it's brighter looking up than it is looking down. Well, that makes sense. And then once again, here's a little fluorescence bump out here. Yeah, Ben.
So what's with the negative to 0? Or is it, I can't tell what this graph, is it symmetrical around?
No, if the sun were straight overhead, it would be.
Okay.
But if the sun's out here, I don't know if I said where it was, but let's say it's at 30 degrees, then this bump will be off a little bit. And you get out your ruler and stuff, and it's really maybe at 120 or something like that. As it goes deeper and deeper, this peak will go to being straight overhead. We'll mention that a little bit later because the scattering redirects the light, and eventually, if you're down at 200 meters, all you can say is it's brightest that way and darkest that way, but you've lost the information about where the sun was due to scattering. Now, and this was at 10 meters. So here's looking upward. Here at 90 degrees, you're looking horizontally towards the sun, and then you're looking downward here. Now, if we do the same plot just above the surface, it's picked up some other bumps here. So the sun was, I didn't say here, but anyway, you're looking upward, you're seeing the really bright sunlight, and then you look down to sort of horizontally, and then you look down further at an angle of, say, this is 30, say 40 degrees. So you're looking down in this direction, and you see this other spike. That's the specular reflection of the sun off the surface. So this peak here, I'm looking upward at the sun, and this peak here, I'm looking downward at its reflection off the sea surface. And every time you see one of these plots, you kind of have to like stop and say, well, wait a minute, does this make sense? Yeah, I figured out the guy's coordinates and I'm ready to go. Notice here, of course, there's no fluorescence peak out here because I'm really looking at the sky radiance distribution, so no fluorescence in that. Okay, here's another way to plot it. Yeah.
What was the spike at like?
Oh, yeah. You get, if you actually go out, so the sun's over here and you look at the brightness of the sky and it's, it's bright, but then as you get towards the horizon, it actually gets brighter. And that's because of scattering by aerosols and such. So the sunlight goes in over there, it scatters, and you'll actually get a brightening of the sky radiance near the horizon. And you're also, if you look up here, you're going through a certain distance of air. And of course, some of that's scattering the sunlight into you. You go over looking in this direction, you're looking through a lot more air before you get to outer space. And there's more aerosols down low, and that gives you more scattering, and you'll actually get, in many cases, you'll actually get a little bump there. But if you look at the magnitude, this is actually a lot less than specular reflection.
Shouldn't there be two horizon bumps like that?
It's what?
Shouldn't there be two horizon bumps like that?
Well, there is a little bit of one here. If you go to 90 degrees, there's a little kink here, but it's not as much as the one here, just the way it turns out. But yeah, those little bumps are all real. Somebody else? Okay, so here's just another way to plot the radiance. This is one wavelength and still one location above the sea surface, but now plotted as a function of theta and phi. So you're thinking of yourself as sitting at the center of the globe here. You're looking upward here at the very bright sun, and you're looking downward here at the specular reflection on the water surface. So you just have to pick whatever kind of plot meets your needs and go for it. Okay, so this is where Ken will start. Here's the plane irradiance. We've got this detector that's back in our Gershon tube here. Oops. So here's our detector here. Just take off this whole tube that is giving you a collimated measurement. And here's just the very end of our Gershon tube where the collimating tube used to be up here. You pull this thing off, and now you have a little detecting surface here. And this is going to be equally sensitive to light from any direction. So the material itself will detect this light just as well as this light or this light. Now, the catch, of course, is if you're looking straight down on the detector, you see a full surface. If you're looking at it at this angle, it looks like a smaller detector. And if it's at 90 degrees, I don't see the detecting surface at all. So when you measure the plane irradiance, plane because this is a flat or plane surface, you measure for some time, your detector has some area delta A. Now we'll have to put the filter back here and get some wavelength band delta lambda, and you get some amount of energy here, and that gives you the downwelling if it's looking upward and measuring light going downward. The downwelling plane irradiance, which is now just units of watts per square meter per nanometer. And so there's your measurement for the instrument. Now, if you want to compute this, given the radiance, you have to account for the fact that it looks like the detector surface gets smaller as the angle of incidence gets bigger. So what I do is I take my radiance distribution coming from all directions or all downwelling directions, and I multiply by the cosine of the angle from the normal of the detector. And that's really accounting for the fact that my radiance coming from the side is seeing a smaller detector than the radiance that's coming straight down. So if you give me the radiance and say compute the downwelling plane irradiance, I have to throw in this cosine factor, and then I integrate over all the downwelling solid angles, in this case, from theta equals 0 around to 2 pi, and then around an azimuthal direction. So that's how you would compute a plane irradiance given the radiance, but you don't have to mess with the cosine here because this is just measuring whatever's there. Okay, and if I take this instrument and turn it upside down, now I'm measuring light that's going upward, and that's the upwelling plane irradiance. Okay, so here's just plots of ED as a function of wavelength or selected depths, and it looks very similar in shape to the radiance plots, but of course it's different units, different magnitude. Once again, you see a fluorescence bump here. Now, if we plot the EDs as a function of depth for a few selected wavelengths, well, it starts out up at the surface, and here 355, 455, 555, and finally out to 685. And some of these wavelengths, they start out at a surface value and they just keep decreasing with depth at the same slope. These wavelengths out here in the red, they start out decaying very quickly with depth, but then they change their slope. So this curve goes to this rate, this curve, all of a sudden at a few meters starts going down at a different slope than it started out at up here. So that looks kind of weird. So you have to wonder what's going on there and why did these wavelengths out here not do that? This like dark blue curve or the green curve or the purple curve, they have basically the same slope all the way down. So something kind of funny there that you need to worry about, and you'll know the answer by the end of the class. Or you'll be able to simulate the answer by the end of the hydrolite lab, either way. Now you'll also have spherical irradiance detectors. And now instead of having a plane surface, we have a little spherical collector. So these things usually look like little ping pong balls. And they can collect light coming in from any direction with no cosine effect. The cross section of this detector looks the same coming down as it does to this light or this light here. So there, once again, this thing detects the light, it gets inside, it's sort of uniform. You put a filter in the detector here, and you measure what would be called the scalar irradiance. Now, if I put some kind of shield on here that blocks any light from going upward, from getting to the detector, or it's black on the surface, and any light that hits here is absorbed by the shield and not reflected back into the detector, then you get, if it's pointed upward, you would get what's called the downwelling scalar irradiance. So it's looking upward, measuring light going downward from any direction. The same sort of formula as for the planar radiance, except now your detector area is going to be something different. And now if you give me the radius and say, what's the downwelling planar radiance? I'm sorry, the downwelling scalar irradiance. Now I take the radius, I integrate over 2 pi in polar angle, pi over 2 in polar angle, 2 pi in azimuthal angle, but there's no cosine factor here because the size of this cross section of the detector is independent from my viewing direction. The sphere looks the same from any direction. And if I turn it upside down, then I measure the upwelling scalar irradiance, and the sum of the upwelling and the downwelling is just the scalar, which I would measure if I removed this shield here and I just got light going in all directions at once. Okay, there's other terms. There's a thing called the vector irradiance, which is basically, instead of putting an absolute value on the cosine, I just put the cosine in there. And this, if you look at the z component of the vector, it's actually just the difference in the downwelling and the upwelling. So we'll derive later a little thing called Gersham's law. And it turns out if you measure the downwelling and the upwelling planar irradiance, and you measure the scalar irradiance, then you can recover the absorption coefficient just from light measurements. And so it's really the difference in the downwelling and the upwelling, and then divided by the scalar, that gives you the absorption coefficient. And so this ED minus EU is usually called the net downwelling planar irradiance. Then finally, there's this thing with a spectral intensity, which is useful for describing point light sources. So if I have a little point, a very small volume that's sending out light in all directions, then if I just measure how much goes into some solid angle, that's the intensity. So intensity is energy per unit time, per unit steradian, per unit wavelength interval, and there's no area factor there. So a lot of people use intensity, meaning magnitude of the radiance, but you really get hit hard by radiative transfer people. Just call it the magnitude of the radiance, because to them and me, intensity always means energy per unit steradian. And this is what we used in one definition of the volume scattering function, where you think of this little volume of water here scattering light off into all directions, and then you have an instrument, or your instrument is looking at that little volume and saying how much is going into a particular solid angle. That was the intensity. And so the intensity per unit volume, with normalized by the incident irradiance, was the volume scattering function. So that's where intensity gets used. We're not going to really need these things for most of what you do, but you're going to see them in the literature, and you'll certainly see Gerson's law, and that's where those things are. Okay, the final sort of thing that you will see a lot of is PAR, photosynthetically available radiation. All of radiative transfer theory is done in energy units, so watts. If you're phytoplankton, how much photosynthesis you do depends not on how much energy you absorb, but on how many photons you absorb. So to a biologist, what matters is not energy units, it's number of photons. So, and if you're a phytoplankton, you don't care what direction the photon was coming from, you just grab it and you do your photosynthesis. So what's relevant for things like understanding phytoplankton photosynthesis is number of photons going in any direction, and I don't care what the state of polarization is either, just how many photons did I absorb. You get that from the scalar irradiance, so it's going in any direction. This is in energy units, and each photon has an energy of hc over lambda. So the number of photons I get is the total energy divided by hc over lambda, which is the energy per photon. So you get this, and then usually it's all the light between 400 and 700 nanometers. Phytoplankton can use any of those photons equally well to do photosynthesis. Now, it's more likely that the phytoplankton chlorophyll molecule will absorb a photon at 440 than that it will absorb one at 550. But if it absorbs either one, you get the same amount of photosynthesis. Yeah, Anna.
If we're using a scalar irradiance meter, how do you get, sorry, if we're using a planar irradiance meter, how do you get scalar irradiance?
You don't.
So how do
You
you
put
get-
a fudge, okay, if you want to measure the true definition of PAR, you have to have scalar irradiance. Now, because you're not interested in what direction the photon's going. If you plug ED in here, then you're getting only the downwelling light. And there's this kind of weird cosine factor because the light that's going straight down sees the full detector. The light's coming in here sees a smaller detector angle, so it gets counted less. So when you plug in ED here, you're giving full credit to the light that's going straight down, which can cause photosynthesis, but the light that's coming in at 60 degrees doesn't get credit for the fact that in the real world, it can cause or can generate just as much photosynthesis as the light going straight down. So you're getting bad value of PAR. Now, having said that, I bet you 9 out of 10 papers where they say we measure PAR, they use a plane irradiance meter here. And the reason is because they're cheap to build and they had one. So they stick in ED here, go through the calculation, and you get PAR, which is always going to be less than the true par because of that cosine factor. How much less? One day it's 30%, one day it's 40%, one day it's 27%. And you don't know how much less because you didn't measure the full radiance distribution. Yeah,
So is the reason we don't off-block as much as don't use scalar and radiance because they're more expensive?
they're harder to make, harder to calibrate. And now the terrestrial people, they often have a little par ball on a stick. And so you'll have this little like stick and there's a little like marble thing out on the end. And they'll go out and they'll stick that down in their plant leaves or whatever, and they'll measure true par. But that just to do a scalar irradiance sensor underwater is just a harder, much more expensive thing to do. Yeah, Ben.
So when you have the ball, scalar, even if the ball is only pointed up and there's a blank surface pointing up.
Yeah. Then what you ought to do, you're measuring E0D. You ought to make the measurement looking upward and then looking downward and add the two together. Or you take the shield off, which is what you really want to do.
How can you take the shield off?
Well, you just think of having this little instrument here with its little par sensor out here, and there's no shield across. Like here's my sensor here, and I put the shield here so it blocks any upwelling light or blocks any reflected light. So now I'm getting E0D, but if I just take this off, I can also get the light that's coming here, hitting my little ping pong ball. Ideally. Now, of course, you always have some loss from the little handle to stick the things on, and so you got to add some little fudge factor. So what the ecosystem modeling people often do is they say, well, I used ED here, and I know that's wrong, but I'll put a fudge factor on it of say 40% more or 30% more to try to give me a better par value. Or what I've often seen is they run their ecosystem models based on par computed from ED, and they just have some fudge factor in the ecosystem model that sort of increases the value a little bit. But that's always a little iffy because all you can say is that par computed from ED will always be less than par from scalar. And when you run Hydrolite at the end, there's a table that says, here's par from ED, here's par from scalar, and you can see, and here's the ratio, you can see how big the error was. And how big the error is depends on the IOPs, the sun angle, and all these other things. But yeah, good question. So I always call this true par, and if it's an ED, I call it a broadband irradiance or something like that, but it's not really par by the definition. Okay, and then we've now turned this into photons per square meter per second. And so rather than giving some number like 10 to the 20th, they usually express it in micro Einsteins per square meter per second. And an Einstein is 1 mole of photons, or Avogadro's number of photons. So you'll see par is usually some number like 1,000 micro Einsteins per square meter per second. But that's just to get a convenient scale on the numbers. Okay, a few more warnings on terminology here. The atmospheric people call our spectral irradiance, they call it specific intensity, and that goes all the way back to Max Planck. And our irradiance, they call flux, but some of them call it flux density. And then you go to the medical field, they'll talk about things like the fluence and the fluence rate. And you're like, I have no idea what these guys are talking about. Oh, well, that's just irradiance and radiance. It's just what they call it. Because all of these fields have reinvented the same wheels for over the last 100 years. And oceanographers won't even talk to atmospheric people, let alone talk to medical people. So nobody knows what the other community is doing or what notation they use. And I remember one time when my wife was getting radiation treatments, and I asked the doctor, I said, what level of radiation is she getting here? And he gives me some number and some units I've never even heard of, because I'm coming out of the physics community and I know how I measure radiation. And he's measuring the same thing, but it's an entirely different terminology. And I have a friend that's a radiologist, and she has no idea what I'm talking about, and vice versa, because we have different terms. So there's a lot of good work in these other fields. You just have to be a linguist to translate back and forth between them. The other thing is we're always talking about spectral irradiance, that is per unit wavelength interval. But your instrument, let's say your satellite radiometer or whatever, or your instrument in the field, it's maybe measuring over a 10 nanometer bandwidth. So you take the spectral value integrated, say, from 410 to 420. Well, this guy is watts per square meter per nanometer, integrated over, say, 10 nanometers. And now you get watts per square meter for a broadband measurement. And all I can say is units and magnitude matter. I have more times than I count had somebody send me an email, say, well, I measured all these measurements and I measured the downwelling planar radiance, and hydrolight's off by a factor of 10 or 100. So hydrolight's a piece of crap. Well, and then I say, well, what units is your instrument putting out? And the answer every time, I swear, from the scientist is, quote, I don't know, I'll have to ask my technician. And then they come back, and then I ask them, what's the bandwidth of the instrument and all that. Then they come back, well, I'm measuring watts per square meter per nanometer. And then their instrument is measuring watts per square centimeter per micrometer, or milliwatts per square meter per micrometer, or whatever. And there's the factor of 10 and 100. So it always works out that way. So you really have to know, you've got an instrument, you've got to go look at the fine print, figure out what's the bandwidth. Is it watts per square meter or watts per square centimeter? Is the wavelength interval per nanometer or per micrometer, or what? And it doesn't really matter. You just have to know what it is, so you can then go compare with hydrolite, which is always in SI units of watts per square meter per nanometer. Okay. My story for today, I decided 9 years ago to go see if there was any good kayaking in Panama. So we flew down to Panama. Here's Panama. Here's the canal. Flew into Panama City here. We took a little plane over to here, and there's a whole bunch of islands off the Caribbean side of Panama. And so we spent, I think it was 9 days kayaking from here back to here to the nearest road, and then we drove back to town. Turns out that, you go back to 1500, the Spanish are coming over, they're taking over Mexico, Panama, Peru, everything. Long story, you know it. There was a tribe of Indians here called the Kuna, and they just had greatest time sticking poison arrows in the Spaniards. And the Spaniards were never able to conquer the Kuna like they did the Aztecs and the Incas and so forth. And it turns out there was no gold here. So the Spaniards just said, these guys are bad news, just leave them alone. And that went on for hundreds of years. And finally, in the 1920s, 27 or so, there was some kind of little move by the Spanish part of Panama to some way take over this area of the Kuna Indians, and the Kunas fought back, and they won the battle, and they finally cut a deal with the Spanish government of Panama, or Spanish descendants. And the deal was, you just leave us alone over here. We're going to run our own show. In return, the Kunas do not vote in Spanish or in the Panamanian elections. The Panamanians do not run their government. The Kuna do not pay taxes to Panama. They really are running their own show. So to go over here, we had to get permission, not from like some Panamanian National Park or something. We got permission from the Kuna Indian tribe to go over there. And then you have to have a Kuna along with you on your trip and all that, which is all perfectly fine. And that keeps the vandalism down. And the Kunas are perpetually being pressured to like put in luxury hotels and golf courses and all this. And they say, we don't want any part of it. We've been doing just fine for 10,000 years. And so we kayaked along here, and there's just like dozens of these little islands. And you notice here, there's a little thatched hut here and a bunch of coconut palms. So the way it works is a family will be assigned an island, and they get it for, I think it's 5 years. And their income comes from selling the coconuts. And then after 5 years, they have a big drawing and they switch all the islands around with different families. So no family is stuck permanently with a good island or a bad island. So it's a very like evil socialist, almost communist thing that we could never have that in America, but it works just fine for this guy. And then when you pull up one of these islands and you say, can I camp here? He'll say, sure, $5 a head, you know, best deal in town. The other thing that's pretty funny is, where does this guy get fresh water? It's in the middle of the ocean on a little sand island. It's like 3 feet above sea level. It turns out that under each of these islands, there's a lens of fresh water, because in hurricane season, or the rainy season, the rain comes down here, it soaks through the sand. Fresh water is lighter than salt water, so it soaks in, and you just get this little like weird lake of fresh water. And you can go up on this island and you can dig a hole 2 or 3 feet deep, and it's fresh water. It's amazing. So that's what the coconut trees in the sky are living off of. So anyway, it was a great trip. Lots of other stories to tell, but it's coming up now 10:30. So I will let you go for the day and turn it over to Kim. And incidentally, I went down here, you know, took all these malaria pills and everything. We didn't see a mosquito the whole time because we were offshore. So we had the trade wind, continuous trade wind blowing all the time, and not a mosquito to be seen. Yeah. Yeah, I can't read that. There anyway.